All right, so we've come up with this idea of Q double prime being equal to H times delta T, at least in systems that are primarily governed by convection, or phenomena that we can describe as happening between two distinct objects. And now that we've come up with this equation, it's important for us to be able to very quickly apply it to a real system to be able to understand, well, how do we even describe, physical systems using this kind of in development theory of heat transfer, right? In particular with the equation that we found before, that Q double prime is equal to H times delta T. So how do we do it? Well, I thought that one great example that we could do to learn how to do this is to talk about what to me is the most important system that is governed by the laws of heat transfer, which is the human body. And in particular, to try to understand the role that metabolism plays in describing the physical properties of the human body as they relate to warmth or coolness or whatever. So here is the physical setup. You are a person, all right? And most people usually have kind of an internal temperature regulation system that keeps us around a temperature of approximately 98.6 degrees Fahrenheit or 37 degrees Celsius. Now, this isn't true for everybody. Some people have a lower resting temperature than others. Some people have a higher resting temperature. Sometimes if we are exposed to environments or pathogens, like our body temperature may, increase or decrease for some periods of time. But most of the time, and certainly for the purposes of this exercise, we can assume that the human body really likes being at a constant 37 degrees Celsius, okay? So this person, which we are going to treat like the object in the interest of this exercise, we are going to say that this person has a temperature of 37 degrees Celsius. That is just constant over time, all right? Now, one of the very interesting things about the human body is that even though we really like having an internal body temperature of 37 degrees Celsius, we really don't want the surrounding air, the stuff that we are surrounded by, we really don't want that to be 37 degrees Celsius, right? If you dump me into a place where the air temperature is 98.6 degrees Fahrenheit or 37 degrees Celsius, I'm going to say this is way too warm. It's way too warm. Curiously, human beings in general like to be surrounded by air that's at a temperature that's much lower than 37 degrees Celsius. And although it will depend based on the kind of person that you are, in particular your physical characteristics and things like that, most of the time, the human body likes to be surrounded by air that is at room temperature, which we can say is somewhere on the order of about 22 degrees Celsius. Now, people will shift this up or down a degree or two, but it doesn't really matter too much. The point is that the human body really likes to stay at 37 degrees Celsius, but really likes to be surrounded by stuff at 22 degrees Celsius. Now think for a quick second about what that means. What does it mean for this to occur from the perspective of what we've talked about in heat transfer? Well, let's follow it to its logical conclusion, right? If we treat the human body like an object that's surrounded by air, the temperature of the human body is larger than the temperature of the air, which means that based on this postulated study, this field of study that we're creating, that there has to be thermal energy, heat, that's being transferred between the human body to the environment, all right? Now, hypothetically speaking, based on our initial theories of how heat transfer works, we would say, well, eventually, this temperature of 37 degrees Celsius is going to drop down to 22 degrees Celsius. And eventually it will, right? At points where it's not going to matter that much for our comfort, okay? But the fact of the matter is, while we're alive, this temperature stays at about 37 degrees Celsius, okay? So how do we reconcile the fact that somehow this temperature is staying the same for the entirety of our lives, for the most part, but that there is this imbalance of temperatures and therefore, hypothetically speaking, a transference of heat that's occurring between the environment and, the human body. So, in order to set this up, let's start to write down some other key facts about the human body, okay? Key facts, and we're just going to assume this for this specific person, but even though we can say that this is approximately representative, it doesn't necessarily have to be, right? People have different bodies, so it doesn't really matter what numbers you pick. We're just picking some numbers and going with it. So we can approximate the surface area of the human body, of this person, as being about, maybe 2 meters squared, okay? As technically speaking, a little large, doesn't matter. We can also say that the approximate volume of this human body is about 0.1 meters cubed, okay? Once again, the precision of the numbers don't really matter. People will have different bodies. It's just to put down a specific set of numbers that will make the math easier, but also give us a representation of the order of magnitude of the quantities that we're going to pull, okay? And so if we treat the human body like this object, right, if we create this volume that we represent as the human body, that we find that that volume is going to be about 0.1 meters cubed, and that the surface area of the boundary between the human body and the environment is about 2 meters squared. Okay? So that's what these things mean. So we know the temperatures, and we know these geometric properties. But there's something else that's useful for us to know, and it is key to understanding exactly how it is that the human body is able to achieve this feat of staying in thermal imbalance with its surroundings. And it's that the human body is constantly transferring heat to the environment. This should not be that much of a surprise to you based off of the logical conclusions that you would pull from this setup, right? If we have a constant temperature imbalance, that means that there has to be a constant heat flux and a constant heat transfer rate between this human body and the environment. And just like before, it depends on the person, but a representative number, an approximation of what that heat transfer rate is for a human body, is about 80 watts. So the human body, approximately, burns 80 watts, 80 joules a second, just off of thermal energy that it's using to somehow preserve this thermal imbalance. Okay, so 80 watts are being transferred from the human body out to the environment. So the questions that we can ask ourselves here are the following. 1, what is the primary mode of heat transfer? That's question 1. Question 2 is, what is the heat transfer coefficient between the human body and the environment? Okay? And then the third question is, what is the amount of volumetric thermal energy generation? What is the Q dot inside of the human body required to keep this whole setup going? Okay? So that's what we have to try to investigate now, these 3 questions. So we can answer the first one right off the bat. What is the primary mode of heat transfer? Well, this human body, which, although it's a murky answer, technically speaking, is a solid, is surrounded by air, right? Which is a gas, which is a fluid. And so as a result, we are describing heat transfer that's occurring between a solid object and a fluid. And so as a result, the primary mode of heat transfer is convection. Okay, so we would describe this as a convective system. Now that doesn't necessarily mean that conduction or radiation aren't happening inside of the system. In fact, when we started to grapple with answering those sorts of questions, we kind of said, nope, this is too tricky for us, we'll just deal with it later. But the point is to basically say that the primary mode of heat transfer is convection because of the fact that we have a solid and a fluid in contact, okay? That's our kind of very primitive understanding of heat transfer modes. So we already have this one checked out. Now we have to answer, what is H, okay? Well, how do we figure that out? Well, the way that we do this is by writing down some of the equations that we had established before to describe heat transfer inside of systems, okay? So we had said that for convective systems, Q double prime is equal to H times delta T. That's equation 1 that we're going to use, right? And the thing that we have to try to figure out is the H. Now we know the delta T, but we don't know the Q double prime, right? Because we have information about the net heat transfer rate that's happening over the entire body, but we do not necessarily have information about what the individual heat fluxes on each piece of the body are. And so we have to try to answer that question. So how do we answer that question? Well, we have to understand how we relate this Q double prime to this quantity, to the heat transfer rate that we do know. And I'll just remind you that Q, the heat transfer rate, is just the integral of those heat fluxes over the surface area that we're considering, right? Over the surface area, the boundary of this object. Now, if we make an assumption, which is to say that we assume that heat fluxes over the surface of this body are all the same everywhere on the body. This is not true, but it's a decent enough assumption that we can get somewhere with the math. Then this integral stops being a nasty integral, right? It just becomes a multiplication, where we are just multiplying the heat flux over any piece of the body, right, because they're all the same, times the surface area of the boundary over which that heat transfer is taking place. And these two things, well, this and this we know, right? We know that 80 watts has to be equal to whatever Q double prime is times 2 meters squared. And so as a result, we can very quickly pull that the heat flux, or at least a heat flux, an average or representative heat flux at any point on the human body is going to be about 40 watts per meter squared. All right? So we've already figured out the Q double prime. We already have the delta T. And so all that we have to do now is to actually go and calculate what that division is by solving for the H. So pardon me that I'm off camera. I'm back. So how do we do it? Well, let's just solve. We go and we say, well, H, if we move stuff around, is just the ratio between the heat fluxes and the difference in temperature, right? We know that the heat flux from what we calculated before was 40 watts per meter squared. And then we're dividing by this temperature difference, right? So by 37 degrees Celsius minus 22 degrees Celsius. And this difference is 15. So when it comes right down to it, H is just 40 watts per meter cubed divided by 15 degrees Celsius, which results in a heat transfer coefficient of 2.6666 repeating. And I'll write the units down here, watts per meter squared degree Celsius. Okay, so this is the answer to number 2. Okay, and we got it by noting that Q and Q double primes are related via either integration or multiplication of surface areas, and that we can use the equation Q double prime is equal to H times delta T to find that H. All right, so that is how we get to part 2. So how do we solve part 3, right? What was part 3? Part 3 is trying to figure out the volumetric energy generation that is required in order to keep our bodies going. And this question is a bit more subtle. So how do we even address it? Well, consider this object, or the region that this object occupies, as what is often referred to as a control volume, okay? Let's just think of it as a volume in space, okay? And we can think about a bunch of different things that are happening to the thermal energy that's located inside of this volume, okay? We can talk about how much thermal energy is in there, but we can also talk about how much thermal energy is moving in or out, how much the thermal energy of this system is changing, all right? So let's suppose that we wanted to understand the thermal energy of this system, right, of this volume. What is that thermal energy? And even though this is a very interesting thing that we'll be doing later, right, we have to come up with an expression of what the thermal energy is as a function of temperature. It is also true that for the purposes of what we're going to do now, it doesn't actually matter very much. Because the only thing that we really care about is the transference of thermal energy, right? We don't actually care about how much thermal energy an object has. We care about how much of that thermal energy is moving around between different objects. And so what we care about is not necessarily the thermal energy of this human body, right, or of the volume of space that the body occupies. We care about how much that thermal energy is changing in time. So I'm putting a dot over it to represent a temporal derivative, but really you can just imagine that this is like dE dt, okay? And so what we want to try to track is what is the rate of change of the thermal energy of everything that's inside of this volume. And I'll give you a second to think about it. Remember that this is just a human body that's located at a fixed temperature of 37 degrees Celsius. I should say is at a fixed temperature of 37 degrees Celsius. Okay? Because it has a constant temperature, it should be the case that it also has a constant thermal energy too. And as a result, the change of the thermal energy of this system should be zero over time, right? And so this thing should be zero. But hypothetically speaking, what are the things that are going to contribute to this change in energy in general, right? So we already know that the change of thermal energy in this specific system is zero. But what could be the things that contribute to its change? Well, here's one thing. You can imagine that there is thermal energy that flows in, right? That is transferred from the environment down to the object, in this case, the human body. You could also imagine that there's thermal energy that's being transferred from the object out to the environment, okay? And you can also imagine that there is maybe some thermal energy which is being generated. And so what this equation over here, which is a very useful kind of tool to keep track of what's happening inside of our systems, right, inside of regions of space, is to say that the thermal energy, the change in the thermal energy of this region is equal to how much is going in minus how much is going out plus how much is being generated. All of these quantities being rates, right? And so for this specific system, when we analyze it, we see, well, the temperature is constant. The system is equilibrated, what we usually refer to as being in steady state. And because the system has a constant temperature, then this thermal energy change is zero, okay? The thermal energy of the system is zero. One thing that I'll mention, I'm using the word equilibrium a little bit loosely. There's a lot of people who like to say that, oh, equilibrium is only true when nothing's moving around. In this case, we'll see that stuff is moving around constantly, but again, distinctions are minor. Is there any thermal energy moving into the system? Is it going into our little region of space? And the answer is no, right? Because we already postulated that from how we're describing heat transfer, thermal energy moves from hot to cold, right? From high temperature to low temperature. And so because the human body's at a uniform 37 and the atmosphere is at 22, then necessarily it must be the case that there's no energy going in, right? There's no transference of thermal energy that goes into the system. So both of these things are 0. What about the energy going out? Well, this is not 0, right? Clearly, there has to be a change or a transference of energy that's flowing out of the human body out into the environment, because that's how we describe the heat transfer, right? There's an imbalance in temperatures, and so therefore, there has to be some energy flowing out of the human body into the atmosphere. And what is that flow out? Well, think about it. This is a change of energy per unit time that is describing how much energy is being transferred from the human body out to the environment. What does that sound like? It sounds like it's a heat transfer rate, and it is. So this thing right here is just what we had labeled Q before. Okay, this heat transfer, this Q, the heat transfer rate of 80 watts, is how much energy the system is transferring out to the environment. The thing that we don't know is, what is this net volume, like net energy generation term? Like, how much energy does the body need to be generating, how much thermal energy, mind you, in order to be able to stay at these conditions? And we will figure that out by taking a look at what happens when I simplify this equation up, right? So we have both of these terms gone. And so what we're left with is E dot gen minus Q is equal to 0. In other words, E dot gen, the energy generation rate inside of our human bodies, has to be precisely equal to Q, which has to be precisely equal to 80 watts, okay? So if we are constantly emitting at a rate of 80 watts, we have to be generating energy at a rate of 80 watts too to compensate, to be able to stay at this temperature forever. But that's not quite the answer, right? Because this is the energy generation, but we also have to talk about the volumetric energy generation. And how do we relate the net, the energy generation to the volumetric energy generation? Well, we just take that volumetric energy generation Q dot, or volumetric energy generation rate, multiply it by the volume of the human body, and then get 80 watts. And so by saying that the volume of the human body, as we stated before, was on the order of about 0.1 meters cubed, we obtain the Q dot, the amount of thermal energy per volume that our body needs to generate in every little piece of our, body per second. This rate is just 80 watts divided by 0.1 meters cubed, which is 800 watts per meter cubed. And so our body needs to continuously transform other kinds of energy into thermal energy via a volumetric, energy generation process that pulls out, approximately 800 watts per meter cubed everywhere in order to be able to keep us at this temperature of 37 degrees Celsius. How does the body do that? Simple. It converts chemical energy from the process of us digesting our foods and bringing in protein. It converts all of the chemical energy that is unlocked as a result of the consumption of food. It converts it into thermal energy, okay? And that thermal energy then goes to power the internal thermostat that keeps us at 37 degrees Celsius. And so now you know a little bit more about how the human body works, in particular the metabolic process. You have some numbers to consider, but also hopefully now you have an understanding of how to take systems where you can define a clear boundary between one thing and the other, and then do some math to try to understand what is the heat transfer rate from one object to another, what is the heat transfer coefficient, based off of algebraic manipulations of quantities that you already know. All right, so this approach works just fine when it comes to dealing with objects that are clearly definable, right? So the human body is very different from air. And so it makes sense to be able to define this region. But what happens, for example, if we start to consider heat transfer that's happening between the top of the human body and the bottom? Or, for example, what happens if we're considering heat transfer that's occurring between one side of a block and the other? In that scenario, we're going to find that the model that we've constructed, the equation of Q double prime is equal to H delta T, is not going to be enough. And we're going to need to create another equation that's going to help us try to model those scenarios in particular. But we'll get to that next time.